everyone, my name is Debbie and I'm a technical development specialist at CelluForce. Today I'm going to present a very fun and valuable piece of work that we have accomplished during the COVID-19 pandemic. It is developing hydroalcoholic gels with CNC. And this project is our effort to help relieve the severe hand sanitizer shortages during the crisis. The work was initiated in March 2020 when the first wave of COVID-19 really hit us unprepared. All of a sudden, the demand for disinfecting gels skyrocketed. What's worse is that the supply of a key thickening ingredient, carbapol, is in severe shortage. Because of this, many places were using watery hand sanitizers that when you pump, you almost have to catch the liquid fast and apply quickly too before it drips. In a typical hand sanitizer formulation, as I listed here, carbapol is the most commonly used rheology modifier. Because it is cross-linked polyacrylic acid, some base in the formulation is used to neutralize the pH. Emollients such as glycerin in the formulation is to prevent the dehydration of skin due to alcohol. And our goal is to see whether CNC can replace the carbapol and still make a good gel hand sanitizer. But before we dive in, let's think about what makes a good gel hand sanitizer. First, it has to reach the alcohol concentration required to disinfect. It is easily dispensable from the bottle. The gel has the body to stay on your hand after pumped. It can be spread smoothly on your hand, and it covers well. It doesn't dry out your skin, and it is cost effective. Preferably, it also uses sustainable ingredients. Well, I'm really glad to say that our initial goal was well reached. CNC was proved to be an effective gelation agent in making hacks. The CNC hand sanitizers were successfully launched on the market, and CelluForce NCC is now officially listed as an alternative rheology modifier for hand sanitizers on the Government of Canada website. The recipe for making a basic CNC gel hand sanitizer is simple. Just water, CNC, and alcohol. A typical formulation contains 1 to 2% of CNC and above 62 weight percent of alcohol, which is the requirement for hand sanitizer, and the rest is water. The preparation is also simple and only requires mixing. However, it is very critical to have the correct sequence of addition. You need to have a well-dispersed CNC suspension in the water phase before adding in the alcohol. With all the success we have made so far in making the CNC gel hand sanitizer, we want to dig deeper and understand why CNC is able to induce a gel in the water alcohol mixture. We then prepared a series of CNC hack samples of different CNC concentrations, of different alcohol concentrations, and even of different alcohol types. And we then leave the gels undisturbed until reaching constant viscosity before being characterized. The first finding is that when we keep the CNC concentration the same at 1.4%, the gelation only happened beyond a certain alcohol concentration of 59%. In the viscosity profile, we can see a three-stage change with increasing alcohol concentration. The first stage is where the concentration of alcohol is low. There is barely any increase in viscosity. Stage 2 starts from 59% and the viscosity sharply increased until reaching the maximum at 68%. In the third stage, further increase in the alcohol concentration only leads to a sharply decreased viscosity. Another thing to notice is that the turbidity of the sample didn't increase much until passing the alcohol concentration where the maximum viscosity is reached. From the gel picture underneath, you can also see that the gels in the third stage start to become really opaque and sort of granular looking too, and definitely much weaker. Further rheology measurements were performed to see this liquid gel transition process more clearly. I draw an illustration here. This shows the top-down view of the testing setup. Our gel sample was loaded inside a cylindrical chamber where a measuring bob was fully immersed. During our test, the bulb will agitate the gel in a rotational oscillation fashion. And there are two parameters that will be measured, storage modulus and loss modulus. Storage modulus is the ability of the sample to store deformation energy or to resist deformation. This shows the elasticity property of the sample. Loss modulus is the ability to dissipate deformation energy, and it shows the flowability of the sample. To better illustrate this, water is a liquid, so it's very flowable, therefore it is higher in loss modulus. Jello, on the other hand, has higher resistance to deformation, therefore is higher in storage modulus. In rheology, 10 delta, which is the ratio of loss modulus to storage modulus, is often used to indicate whether the sample is more liquid-like or more solid-like. And from the 10 delta plot, which is the red curve shown in the plot, you can see clearly that starting from 59% alcohol concentration, the mixture turns from being watery to being jelly. This further confirms that beyond 59%, the mixture has reached the gelation state. We then imaged all the samples through the polarized light to check up on CNC and see how they're doing during the process and whether that can help us explain the gelation behavior. Interestingly, the three stages that we saw earlier in the viscosity profile actually matches three different CNC dispersion states. In phase 1, the CNC shows an anisotropic, well-dispersed state, where we can barely observe any birefringence pattern. The mixture is also a liquid-like sample. In phase 2, we can clearly observe the birefringence color throughout the gel. This is very critical proof that CNCs are forming isotropic domains in the mixture during this smooth gelation stage. And we can definitely relate the isotropic domains to the formation of this jet gelation. And finally, in the third stage, at higher alcohol concentration, we lost the birefringence pattern again, and the gel has high opacity. This suggests that CNCs are in aggregated phase. Based on our test and observation so far, we made a hypothesis that CNC hack gelation is driven by a water depletion mechanism. We believe that in the ternary system of CNC water alcohol, CNC and alcohol molecules compete for water because they both need water molecules to form a hydration layer to stabilize. When we have higher alcohol concentration, there's less water molecules available for stabilizing CNC. Therefore, CNC particles were forced into forming the chironematic domains in order to minimize the amount of water needed on the surface. And more domains eventually form the percolation network. That's when the gelation occurs. To validate our theory, we have done extensive research to find us evidence. The two papers listed here are the critical proof that alcohol and water mixture is not a homogeneous system. Instead, alcohol molecules tend to form clusters with certain amount of water molecules forming hydrogen bonding around the clusters to stabilize. The other support we found is from the work done by a Japanese group, where they also have observed similar viscosity change and gelation behavior of clay nanosheets in the water alcohol mixtures. From their experiment and observations, they proposed that the gelation was induced by the network formation of clay nanosheets at high enough alcohol concentration where the water is exhausted. Their theory is agrees well with ours, and it's just in our case, it is the network formation of chironematic CNC domains that induce the gel. We further expand our theory and test the CNC hack samples using 3 other types of alcohols, and the gelation all happened beyond a certain alcohol concentration. Moreover, we found that the gelation concentration required to form a gel is related to the hydrophobicity of the alcohol. In the table, I listed the octanol water partition coefficient for all 4 alcohols. The higher the value, the more hydrophobic it is. From being the most hydrophilic one, methanol, to the most hydrophobic one, butanol, we have seen a decreased alcohol concentration required to induce a gelation. This is because more hydrophobic alcohol requires more water molecules to stabilize. Therefore, it has more power. It is more powerful in exhausting free water molecules. Therefore, can induce the gelation at a lower alcohol concentration. We further compared the viscosity and turbidity results for all CNC hack samples made with 4 different types of alcohols, and they all show very similar patterns of change, although the change in methanol system is less prominent compared to other alcohols, presumably because this is the most hydrophilic alcohol of the 4. As mentioned earlier, both CNC and alcohol can consume free water molecules. So theoretically, we can also adjust the CNC level in the mixture to tune the gel property. Indeed, when we keep the ethanol concentration the same, but gradually increase the amount of CNC in the mixture, the viscosity shows a sharp increase beyond 1.4% until reaching the maximum at 2.6%. The viscosity further drops beyond this concentration of CNC, and we can also see a very aggregated and opaque gel. And if we compare the results with a control sample, which is the CNC prepared at different concentrations in just water, there's no such change can be observed for either viscosity or turbidity. This confirms that the gelation behavior is unique in the CNC alcohol water system, and this is due to the inhomogeneous mixing of the alcohol and the water. Now that the science behind CNC hack formation is clear, we can play with the ingredients to customize our gel recipes. Take one of the super liquid-like sample we made at 39% ethanol, for example. If we bump the CNC concentration up from 1.4% to 3.5%, a very strong gel can be induced. Same thing in the right example. If you want to keep the CNC level low, just increase the ethanol concentration to gel it up. And if you remember the standards we lay out in the beginning, it takes more than a gel to be a good hand sanitizer. The gel also has to be easily dispensable and applicable on the skin. And thanks to CNC, all the CNC hack samples inherit the shear thinning behavior. Upon applying the shear force, the viscosity drops significantly. Another property we want to further evaluate for CNC hack is the speed of recovery. The results was plotted on the left picture, and in this test, the viscosity of CNC hack was first measured at low shear rate for 3 minutes. Then the gel was completely disrupted with high shear mixing for 2 minutes. We then turned down the shear rate again to measure the recovered viscosity at low shear rate. You can see that the viscosity bounced back up quickly to a decent level right after we stopped the high shear mixing. Further on-hand test confirmed that the CNC hack stays well on the skin after pumped, and after spreading, it can cover your hand really well too without overflow or dripping. Finally, I would like to conclude my presentation by revisiting this list of standards we set and see whether now we can check all those points. First, we have demonstrated that a nice CNC hand sanitizer can be made at a required alcohol concentration. Then the shear thinning behavior of CNC hack gel makes it easy to dispense from the bottle and spread it evenly on your skin. Because the gel also recovers fast, so it has the body to stay on your hand after pumped, and during spreading, it doesn't drip or overflow, and it can cover well on your hand. In terms of emollient, actually, thanks to the CNC, we don't need emollient to prevent skin from drying out, because during drying, CNC naturally form this biofilm to preserve the natural moisture from your skin. Cost-wise, although CNC is more costly compared to carbopol, but we did save on the neutralizer and emollient. And plus, CNC is a natural, sustainable material with lots of health benefits. So it is not that expensive, and it is particularly a better option for luxurious brands. Thank you so much for having me today, and that's all for my presentation. I hope you found our discovery exciting too, and I'm more than happy to answer any of the questions that you might have.